System architecture consists primarily of a virtual plant environment that interfaces externally via Modbus TCP server platform. Digital and analog variables within the Modbus registry are internally mapped to real-time, dynamically reactive graphical objects or GUIs within the virtual plant. Modbus clients originate from either software or hardware platform like a PLC, connecting to the server to alter the respective I/O. The generated virtual plant in this scenario mimics a single tank level control system with an operator control panel. Important to highlight that the intelligence to run the system will be externally sourced by the Modbus client. Respective GUI elements, like the valve, only respond to variable changes within the I/O Modbus registry, hosted by the server. The operator control panel consists of the following: start and stop push button input signals, DI0 and DI1, pump run LED status output signal, DQ0, current tank level segment analog display value, AQ3, desired set point tank level segment analog display value, AQ2, and the potentiometer that is used to adjust the desired set point, AI2. The tank level configuration consists of the following: a linear tank with a side glass fitted with a level transmitter, AI0, flow transmitter mounted on the outlet, AI1, inlet and outlet actuated control valves, namely AQ0 and AQ1. The Modbus TCP server will drive all the respective internally mapped I/O variables. For example, the change to AQ0 will alter the respective position of the inlet control valve between the maximum open and closed positions, which in turn changes the flow rate of the water into the tank. When an operator presses the start button on the control panel, for example, the state will change from open to a closed contact. Node-RED is used as the logic controller in this case, which in effect is the brains of the plant's logic. Node-RED can either be loaded on a Windows or on a Raspberry Pi platform, providing the graphical user interface, the GUI, and connects to the server as a client using Modbus TCP. The level in the tank is termed the process variable, PV, while the desired value is termed the set point, SP. The final control element used to maintain the level in the tank is termed the manipulated variable, MV, in this case the inlet control valve. The difference between the PV and SP is termed the error, expressed as a percentage. Response is charted to monitor and tune the system over time via the PID settings, which is used to achieve the optimum response curve, known as quarter wave tuning. A customized built-in proportional integral derivative or PID controller is utilized to control and manage the tank level to the desired value. The PID loop uses the level transmitter as the input, while the input flow control valve as the output. The set point determines the tank level target value for the PID algorithm, which must compensate for changes in load demand. The load demand in turn is manually changed via the outlet control valve. The algorithm must be able to balance the supply against the load at all times in order to maintain the level at the desired value. Run mode in action. The implementation of an industrial programmable logic controller, or PLC, to interface to the virtual plant environment via Modbus TCP can also be implemented instead of Node-RED, utilizing the same I/O mapping architecture. Thank you for watching.